Okay, great. Hi, everyone. Today we will be having Brendon Boldt, one of the TAs, give a guest lecture. We're going to be talking about margin-based methods and reinforcement learning for structured prediction. And these are ways that you can explicitly train your model so that it achieves the goals you want it to achieve. So up until now, we've been doing things like maximum likelihood estimation that allow you to kind of maximize the probability of the true output, but that doesn't necessarily mean that you're actually going to get a good output when you generate whatever you're trying to generate. So, without further ado, I will turn it over to Brendon, and feel free to ask questions and everything.
So. Yeah, for sure. And also, I got the slides out late, but they're on Piazza, just in case I posted a link to the PDF. Yeah, so Graham kindly already gave the introduction. I'll just, to give credit where credit is due, I recreated the slides in Beamer, but the content is primarily Graham's. But if you see any content that's questionable, maybe it's something I added and didn't check thoroughly enough. So I want to give a quick overview for the lecture just to help you navigate. You can also look at the top of the beautiful Beamer bar there to see where we are in the lecture. So we're talking about prediction today. Now, maybe the simplest kind of prediction we could be doing is something like binary classification. We just have two discrete classes, and we just want to choose one of them. This might easily come about in something like sentiment classification when we want to judge a review or the sentence to be positive or negative. We could easily then generalize this to multiple classes. In this case, we could do three-way sentiment classification, positive, neutral, or negative. Of course, we could go even higher than that if we wanted. And this is not quite as common in NLP to my knowledge, but we can also do regression, which means that we're going to be trying to predict a real number or maybe a vector of real numbers. And we could actually still fit this into sentiment classification. Let's say we wanted to rate the positivity of a movie or a positivity of a review of a movie going from 0 to 1. The sort of catch-all term for all the other kinds of prediction that we tend to find in NLP is structured prediction. To a certain extent, you could see this as having infinite labels or infinitely many classes or exponentially many labels, but it's more than just having that. It's that these predictions usually have some sort of internal structure that isn't just a real number or a sort of set of classes. So we could do this would apply to something like machine translation, where we want to go from, I hate this movie, to ich hasse diesen Film, where the output is a sequence of labels or a sequence of words. And this could be even more explicitly structured if we were going from something like a sentence to the parse tree for that sentence. Today, we're going to focus mostly on generating sequences, as this is the most common in NLP, but a lot of these methods will be somewhat easy to translate to other forms of structured prediction if you should want to do that. So having this sort of structured prediction and doing this kind of thing has some tricky aspects to it. And there are going to be two problems that commonly crop up that I'm going to talk about a couple different ways to sort of address during this lecture. The first problem is exposure bias. So in a sort of baseline maximum likelihood method of prediction, we're going to use something called teacher forcing when we are training like a decoder model. And what this means is that as the decoder produces outputs at each time step, from the previous time step, we're feeding in the prediction from the model, except at training time, we're going to be using the ground truth labels to help speed up training, to give that good signal of predicting like the token at t based on the correct token from t-1. The problem is there's no guarantee of this at test time. Our model is going to make some mistakes, most likely, in which case it's never seen those mistakes during training. And as we know, once your distribution shifts and you haven't really accounted for it, things tend to go downhill. So this is exposure bias, and this is the first problem we're going to be addressing. The second problem is that as Graham said right at the beginning, there's not always a regard for the evaluation metric. When you're just training to maximize the probability of your outputs, that can actually be somewhat different than what you want in the end. And ultimately, we do want good outputs. And this problem doesn't really crop up with something like classification, because if we're trying to maximize the probability of the correct class, this is basically the same thing as maximizing our accuracy, or pretty close to maximizing our F1 score. But we don't really use accuracy, or at least not in the exact same way, if we're doing something like machine translation. Instead, we have these metrics like BLUE or Meteor, which are considerably more complex than just, right or wrong. Thus, the training objective, what we're actually optimizing our parameters to, that is maximum likelihood, is not the ultimate goal. And this also is closely related to the fact that maximum likelihood doesn't take into account how bad certain errors are. When you're doing multi-class classification, again, if you predict a wrong class, it's just wrong. But with something like machine translation, there are errors that can range all the way from minor and barely noticeable to catastrophic. So the last piece of overview I sort of want to give is just sort of a picture that I want you to have in your head during this lecture. And that is the idea of a bias variance trade-off. So if you've taken an introductory machine learning course, there's a pretty good chance they've talked about this idea. And this is sort of a picture that I like to use to illustrate it, at least in my own head. So let's say there's a value that we're just trying to estimate, and that's in black here. This black line is some true value that we want to estimate, but we don't have direct access to. The only way we can start to find out what this value is by taking samples from a distribution. This blue distribution is properly centered on the true value, but it has a high variance. So if we're only able to take a handful of samples, there's a fairly large chance that those samples are going to be far away from the true value, even if we took. And it's only when we take very many samples do we actually get will we actually find the mean with some amount of accuracy. On the other hand, the red distribution is a bit biased. It's actually not centered on the value we want, but it's a lot tighter, has a lower variance, and it might actually give us a better estimate of this true value if we can only take a few samples. So one important part of structured prediction that we're not going to be talking about today, because hopefully you're familiar with the basics of it already, are things like the models that actually do the generation. So this would be like a recurrent neural network for decoding, or a convolutional or self-attentional decoder. And then you could also go more the classical ML route and be using something like a conditional random field. We're going to spend more time today talking about the training algorithms themselves. As a baseline, we're going to be using maximum likelihood with teacher forcing is sort of going to be our implicit baseline, and we're going to be trying to improve and compare against this. We're going to briefly talk about sequence level likelihood and shift that right into a discussion about the structured perceptron and structured hinge loss. Then we're going to kind of change directions, talk about reinforcement learning and minimum risk training. And then we're quickly going to review maybe some simpler methods to remedy exposure bias. Okay, so let's get started talking about margin-based methods. This is going to start by remembering briefly kind of introductory statistics and thinking about normalization. So normalization, just very quickly, is the fact that all of the probabilities of the different outcomes in a given distribution have to sum to 1. So if you have some model which is generating a score, this function here, this score is not going to be normalized. The model is only generating a score for one thing at a time. And so we have to choose how we're going to normalize this score if we're building a probabilistic model. So if we're doing this locally and we're building a locally normalized model, we're going to decompose the probability of a given sequence over each decision. And this is where something like teacher forcing and the bias that it experienced kind of creeps in, because teacher forcing is sort of changing what the model is seeing at each time step during training. This is in contrast with a globally normalized model or an energy-based model. And this is where we're going to be judging the probability of a sequence all at once. We're going to assign a score to a whole sequence, and then we're going to normalize it by every possible sequence in a hope to avoid some issues here to kind of look at the sequence as a whole at once. But as you could imagine, the normalization of a global model is not trivial to do. Whereas with a local model, you might be normalizing over 10,000 words in a vocabulary. With a global normalization, you're going to have to calculate something called the partition function. Oftentimes, you'll see this written as like a z and then whatever inputs there are for the function. But what this usually ends up being is an iteration over, as I said before, all the possible sequences. So this V star set is the Cartesian product of, if you have a sequence length of 20, it's going to be 20 sets, the Cartesian product of 20 sets. And if each set has a cardinality of 10,000, that means that you're going to have to iterate over 10,000 raised to the 20 items. This is exponentially large. There's no way you can do this naively. So we have to fall back to one of two methods for calculating this partition function if we want to use a globally normalized model. If you're using something like a conditional random field where you have a restriction on the conditions, namely like a linear one, it's possible to use dynamic programming and some clever mathematics to actually calculate this partition function without naively iterating through everything. But chances are you're not using conditional random fields as much. You probably want to be using neural networks. I hear that's what people like these days. And that means that you can't use these clever mathematical tricks in dynamic programming, or at least not in most cases. So you're going to have to fall back to this second option, and that's subsampling. So subsampling is just a way to probabilistically estimate the value of the partition function. And there are going to be two ways to do this. And this is the first place that the bias variance trade-off, I think, nicely crops up. So in direct sampling, this is sort of the common sense, straightforward approach. To estimate the partition function, we're just going to sample from the distribution according to the probabilities. We're going to take some fixed number of distributions k, and we're just going to use that. What's great about this is it's what's called an unbiased estimator. That means that the more and more samples you take, as k approaches infinity, you are guaranteed to get the actual distribution. You're guaranteed to be kind of optimizing to the correct objective. Unfortunately, this is a very high variance method. That means that in practice, you're going to need quite a large k before you get consistent enough estimates for it to be useful in optimization. So the other approach is we can maybe try to get something a little bit lower variance, but this is going to bias our model a bit. And we would do something like beam search, or not bias our model, but bias the estimate of the partition function. So we might use something like beam search or other search methods to selectively generate more high probability samples. And when you generate higher probability samples, this is going to decrease the variance, and so you can use a smaller k, but things are going to be biased because you are now selecting things not in accordance with the probability function or the probability distribution, but according to some other criteria. The hope here, though, is that the gain you get from getting a lower variance and kind of tightening up that distribution, that outweighs the fact that the distribution has shifted from where it actually where it truly is, if you just look at the raw partition function or the probability distribution behind that. So leading into the structured perceptron, what if we just didn't do normalization? I mean, probability distributions are nice and there are tons of theories about them and whatnot, but depending on what you're doing, you might not even need a probability distribution. For example, if you're just doing inference, a lot of the time, much of the time, you just want the best output. You just want the argmax. And we can remember here that when we divide by a positive number, which is all normalization is that this is a monotonic operation. So you can see here, we have y hat, which is our prediction that we want. And we're going to find this by taking the argmax of the probability distribution, P, which is normalized. But this is actually just the same as taking the argmax of our unnormalized set of scores. So great, if this is all we're doing, we don't actually need to do normalization. One of the simplest ways to train an unnormalized model is to use what's called the structured perceptron algorithm. And what's nice about this is what you can remember here is since we're using like a capital Y and whatnot, we're dealing at the whole sequence level. So we're bypassing the issue of exposure bias here because we're giving scores to whole sequences at once and training our model based on that. The essence of the structured perceptron algorithm starts with this argmax, where we're going to find the label, which is like a sequence of words or something. We're going to be finding the label, which the model scores the highest, unless it actually scores the reference label the highest, in which case we'll use the second best. But once we have this argmax label, we're going to compare it to the correct label. If the argmax label, which is incorrect, is scored higher than the correct label, we're going to want to adjust our parameters. And we're just going to do this by taking one step of gradient descent. Or in particular, we're going to be descending along the gradient of the incorrect argmax label. So we're scoring that lower next time we see it. And the reference label, we're going to try to score higher. So that's what the two gradient terms in this algorithm are doing. We can express this a little bit more succinctly if we just show it as a loss function. And what you see here is we just have the max of this zero term and the undifferentiated scores. So when you take the derivative of this, this is just going to yield that structured perceptron algorithm you saw before. But it's just what you take away here is that in our loss, we're considering these two examples, the correct label, y, and the argmax predicted label, the y hat. This is just the normal loss function. It's differentiable. And so you can use this in your neural networks. But what this doesn't, or what isn't so nice about this is that you actually need to still go and find the argmax, and you still need to be able to calculate a score for the true candidate. And this means that you have to do prediction. You have to be generating the sequence during training. As you know, neural networks have a lot of parameters, and they have a big output space. And this means that you need a lot of information in your gradient and a lot of gradient updates to actually train these things properly. And so here we realize sort of a trade-off between the algorithms. In the structured perceptron, you're just selecting one negative example. And it's not exactly easy to select many more because remember, you have to be doing this prediction, you have to be generating sequences during training. So although you're avoiding bias in a way here, you are introducing variance by only looking at one sample at a time. Whereas when you're using teacher forcing and we're using maximum likelihood, since this is fully differentiable, it's updating all the parameters at once because if you're looking at something like a softmax, the gradient is flowing backwards through the denominator. But of course, this suffers from exposure bias, as we said at the beginning. What we can do is we're not forced to choose just one of these. We can do pre-training with teacher forcing and maximum likelihood to get our model to a good state quickly, and then we can fine-tune with a less biased objective like this structured perceptron. So far, I've talked about sort of how to address exposure bias with this structured perceptron method, but how might we address the second problem and look at our cost functions? I want to, again, bring you back to your Machine Learning 101 course. If you didn't take it, that's fine. But you've probably seen graphs like this sort of decision boundary between our two classes. And I asked you this question: which is better, the dotted line, which kind of just looks like a line on my screen, oh, it looks dotted there, or the dashed line? I think, but I want to remind you here that both of these, according to our perceptron loss, would have zero loss. These are both perfectly fine solutions. But I think intuitively, we expect there to be some sort of stochasticity to our parameters. And so we want to have as much wiggle room as possible. We'd like to have sort of this margin of error that the dashed line offers us. And this is exactly what we're going to do. We're going to add a margin to our perceptron loss, and this is what we'll call hinge loss. So with perceptron loss, we only penalize an incorrect example when it's scored higher than the reference or higher than the ground truth label. But in this case, with hinge loss, if the incorrect label is even within this margin of the score, we're going to kind of push these farther apart. We're going to raise the score of the reference. We're going to decrease the score of the incorrect label. And so what that yields is actually pretty simple when you look at the loss function down here, and we're just adding m plus our perceptron loss, of course, within the maps and whatnot. So this seems like a nice step forward, but what it is doing is it's basically saying we want to keep all incorrect answers at least this far away, no matter how good or bad the mistake is, or like not so bad versus very bad. And I think it's not hard to see that some mistakes can be worse than others. If we're doing something like part of speech tagging, then if we accidentally, or not accidentally, but the model incorrectly predicts a verb to be, like a non-past, non-third person verb, this is not too bad of an error. But if our model is predicting a verb to be a noun, this could be very bad for downstream applications like a parser or a named entity recognizer. And so, again, as we said at the beginning, we'd like to account for this during our training. And this is exactly what cost-augmented hinge loss does. Now, instead of having our margin be constant, we're going to say we want our margin to be proportional to how bad the mistake is. So if it's not a very bad mistake, our cost function is going to yield a small value, in which case it's going to allow for a smaller margin. But we're going to make a big margin if the difference between the predicted label and the correct label is very costly or very bad. So in here, just in the, when we write this out as a loss function, we no longer have the m, but we have now replaced this with cost, this function, in terms of y hat, the prediction, and y, the ground truth label. As you'll notice, there's no dependence of this cost function on theta. On the one hand, this is good because it allows us to use non-differentiable cost functions. And differentiability is a pretty big, it's a pretty big ask. It's kind of hard to make certain things differentiable. And so this frees us to use some sequence level metrics. But on the other hand, when it's not parameterized, when theta isn't involved, it means that the gradient isn't as informative. And in fact, if we didn't still have these score functions, the s of y hat and the s of y, we wouldn't be able to backpropagate through this at all. So as I just mentioned, we can make the cost over whole sequences and not worry about differentiability. We, of course, could do something very simple, like 0-1 loss, where we have a 1 if the sequences aren't identical, and a 0 only if they're the same. We could be a little bit more clever with our loss and use Hamming loss, where as long as the sequences are the same length that you're comparing, you just add 1 to the cost for every differing element. But you could go even crazier. You could talk about edit distance. You can talk about 1 blue and such things. So when we're looking at structured hinge loss, this cost function is actually going to influence this argmax. So if you remember back, the structured perceptron required us to find the argmax of the model. But now, since we've added the cost function, and this is a function of the prediction that's being made of the thing we're trying to find the argmax for, we're going to have to incorporate this into our search process to find the argmax. So I'll say in certain cases, this is actually very easy to do. In other cases, it's probably very hard, but we'll show you the easy case here. Stay positive. If we're doing something like Hamming loss is decomposable over each word. Just looking at each element of the sequence, if they line up, good, it's a 0. If not, it's a +1. So if we're doing decoding like this, you can see that the correct part of speech tag for I is a personal pronoun, in which case we don't add anything to its cost, but all of the incorrect costs, or all the incorrect labels, which we know because this is being done at training time, we can add a 1 to this. And so the search function can be sensitive to the cost that we've added in the process of training. This is the last slide I have on margin-based methods and like the structured perceptron. So if anybody had questions on this part, I'd be happy to take them. Yeah. So the question was, what's a score function over a sequence? This S function that kept showing up. This is just going to be, this is really an arbitrary function. You could just think of it as some kind of neural network which outputs a real number.
And that's basically right. Like maybe the easiest way to think of it is the sum of the logits for each word in an output. If you're doing like a translation model or something like that, that would be one example.
Oh. Learned in the process of, the question was, can the cost function be learned? And do you mean like learned during the training process? Would this be something like an adversarial cost along those lines? Because otherwise I feel like you would just train your cost function beforehand and use that. But...
Yeah, so that's a good point. Like you could think of three situations. One situation is where you have a non-learned cost function, like 1 minus blue score for translation, for example, or just accuracy, sequence level accuracy, or part of speech tagging accuracy or something. So that would be non-learned. That's defined beforehand. A second situation is where you could learn it beforehand, like Brendon mentioned, and that would be something like any of the learnable metrics that we talked about for machine translation, for example. So there you have human evaluation scores, and you would like to simulate the human evaluation scores. So you learn the regression function to the evaluation score, and then you have your cost function be like 1 minus that evaluation score. And then the final thing is like learning it jointly with the generation model. The conceptually hard thing there is, how do you define the learning signal for your evaluation function, right? For your cost function, like, because you'll need a loss function to train your loss function, basically. So what is that? Generative adversarial networks, which we're going to be talking about soon, is the most typical example, where basically you learn the discriminator jointly with the generator. So that's one example of something like that. You might be able to think of other things, but I can't think of that many other examples of that.
Yeah, so in this case, we're actually, so kind of within the word level, in this instance, Hamming loss isn't actually accounting for this. This is actually accounting for differences in the whole sequence, because during decoding, we're actually looking into the sequence and saying, if you've only made one mistake during decoding, then you're only getting one there, where if you made a lot of mistakes, you would get 1+ for every mistake you made. Of course, you could one-up this Hamming loss if you're doing part of speech tagging and say that, okay, nouns and nouns and pronouns are pretty similar, so we're not going to add a +1, we might add a +0.5 in this case. So at different levels, you could be incorporating different levels of error. Okay, there are just a couple of questions on Zoom that I'd like to address. First is, could you explain again why beam search has lower variance? Beam search has lower variance. I'm pretty sure. If this isn't clear, you can just ask a clarification question here. Because when you're selecting high probability outputs, that's kind of, since high probability outputs are more common, essentially you're going to be clustering those more tightly together. Because if you're just randomly sampling and you happen to get one rare example, it could throw your distribution off a lot. Because, if you're, I guess I don't have a good example off the top of my head, but yeah, you're kind of more susceptible to outliers if you're not particularly selecting for high probability output.
Yeah. And just to give another, that's exactly right, but just to give another example of this, let's say you're thinking about a translation task. And we have, this is a dog. The dog is one of our translations. It's a dog. That's a dog. And then down here you have, it's a cat. Hello. And so basically, if you look at the stuff up top here, this is 90% of the probability mass. And let's say you did a beam search with a size of 3, and you got these top 3 candidates here. You would be covering 90% of the probability mass. And maybe all of these would be good translations, so they would all get a high score, so you would barely update your model. So that's probably good. Oh yeah. So this is so you covered kind of most of the probability mass here. However, if you sampled other probabilities 1 in 10 times, you would get something from this bottom here. And these are bad translations that your model nonetheless is given a non-trivial probability to. So in order to penalize these outputs more, in order to actually downweight them more in continued training, you would have to get these at least some of the time. And if you use beam search, you would be covering 90% of the probability mass that your model saw, but you would never be sampling these lower probability ones. On the other hand, let's say you did sampling, sure, you're going to get the top ones most of the time, but every once in a while you'll get an outlier down here. So maybe you would be getting these strange ones that aren't representative of the distribution as a whole. And that's particularly bad if it's not 90% of the probability mass is concentrated on the top ones, but only 3% of the probability mass is concentrated on the good ones, and 97% is just horrible, useless translations. Then you wouldn't be getting a gradient signal to improve the probability of the good ones. It would be just your model would be seeing, oh, every translation I generate is garbage. I don't know how to optimize my model and upweight anything, because everything's bad. So it's kind of like a trade-off between over-biasing. Beam search will over-bias towards the highest scoring ones, and sampling, if you don't have, if sampling won't give you good things, then correcting for that beam search.
And then another question in the chat is the cost-augmented decoding similar to teacher forcing, since we are enforcing the correct prediction during training. And on one level, I think it's dissimilar because instead of using teacher forcing in sequential decoding, you're optimizing the selection of each vocabulary word. Whereas if we're doing cost-augmented hinge loss, we're still going to be optimizing across the whole sequence, but I might be missing something here. I think it's a good question.
Yeah, and like sometimes when I introduced this slide before, I would call this evil teacher forcing because it's actually doing the opposite, right? Teacher forcing, you're always forced to pick the correct answer. So if you did teacher forcing, you would always be picking personal pronoun here, right? You always pick the correct answer as your previous input. Here, you're actually encouraging the model to not pick the correct answer. You're making it harder to pick the correct answer by adding a score, adding to the score of picking correct answers based on their loss. And so, in a way, by making it harder at training time, you're making it easier at test time because the model has to work really hard at training time to get the right answer. So then test time becomes easier. And kind of an analog to this is dropout. You know, dropout in neural networks, basically you're dropping out some of the representations. You're dropping out some of the representations at training time to make training harder, and in response to that, test time becomes easier. So it's kind of a similar idea.
Thanks for the question. And I'll talk about reinforcement learning. I'm going to give you a bit of whiplash here because reinforcement learning is just a different paradigm, but the unifying parts of these two different discussions is that we're still looking to solve the same problems of exposure bias and working at the sequence level instead of the individual element level. And additionally, and maybe more importantly, we're still hoping to optimize directly against our ultimate goal or our evaluation metrics. So the research that I'm doing for my thesis actually involves a little bit of reinforcement learning. And what this means is that people will ask me, oh, what's your thesis on? And if this is just my neighbor, they might not have a master's degree in machine learning. So I always like to start off with a very simple explanation of what machine learning is. And then I'll make things a little bit more formal so that if you run into this RL again, you can kind of understand what's going on. But still, I'll start with the little story I like to tell. And that reinforcement learning starts with a robot, which we call the agent, that lives in a little world, usually a virtual world, that we call the environment. And things take place in sort of discrete units of time, like kind of ticks of a clock. At a given point in time, the environment is at a certain state. It has a certain state that kind of describes everything in the environment, where the agent is, where any objects might be, if we're still using the robot analogy. And what the agent then does is it makes an observation of this state, and then it will take an action in response to this. The environment will somehow react to this action. If the agent is moving, then the state of the agent will change, like in the environment, or if it picks up a block, that might be reflected. And then based on this action and what state the environment is in, the agent will receive a reward. So a little bit more abstractly, the kind of conceptual objects that we have in a reinforcement learning problem are the state space, S, which is a set of all the different configurations that the world, or really that the environment, whatever that might be, is set up in. The action space is the set of actions that the agent can take at any given time. Probably the part that you're most interested in is going to be pi, which is the policy. And that is a function which takes in the state and produces an action. This is oftentimes in deep reinforcement learning parameterized with, or not parameterized, but like represented by a neural network. Because as you know, neural networks are general function approximators. So the neural network represented by pi is usually what people are most interested in with a reinforcement learning problem. Of course, we still have to define our reward function, which takes in the state and the action, and then will produce a real number, which of course could be 0 or could be anything else. And then just for completeness, if your environment is stochastic, we have what's called the transition function. And this just says, what's the probability of reaching a given state if you took an action last time step with us in a certain state? So if you're in a world where the wind blows stronger sometimes than others, then there might be a probability that you get blown over at a given time step. But this isn't as important in the examples that will follow. So if you read Andrei Karpathy's wonderful blog post giving a quick intro into reinforcement learning, you'll see that he used the example of Pong. And I think this is a great example. Video games make a pretty good reinforcement learning environment. So in Pong, our state space will be defined by the pixels of the display. Or you might say maybe 2 frames of pixels so that you can kind of gauge how fast the ball is moving. But generally, that's the thing which the agent can observe. The actions, of course, in Pong are to move your paddle up or down, and the reward is whether you win or lose. Typically a +1 for winning and a -1 for losing. We could also talk about something like a self-driving car, in which case the state might be the location of your car or the agent's car. The other cars, where the road goes, all the street signs, all these different things you can see while driving a car. The actions would be, how are you turning the steering wheel? Are you pressing the gas? Are you pressing the brake? Maybe you're using, your signals to show where you're going to turn. And then the reward function might be, we're going to give you a big negative reward for crashing, and we're going to give you, maybe small positive rewards for obeying traffic laws. But aside from these kinds of robotic-centric examples, we could also view something like image classification as an example of reinforcement learning. We have to be just a little bit creative, but if we think of the state as the image that is given to the model, the image that's going to be classified, that's the observation being made. The action which the model is going to generate is actually just a probability distribution over the classes that you're going to predict. And then the reward is going to be the probability, or maybe the log probability of the correct class. So reinforcement learning is actually a very general set of methods. But still, why are we talking about reinforcement learning in a natural language processing class? Well, I mean, sometimes we just have situations in natural language processing that look like what I'd call a traditional RL problem. If we're doing something like training a dialogue agent, then we're going to be, our agent is going to take a certain number of actions, which are going to be, producing utterances or responses to other agents in the dialogue. And at the end, it might receive a score based on how informative it was or how polite it was. And reinforcement learning is going to be the primary paradigm by which we train it here. Also things like vision language navigation, where like a robot or a virtual robot has to take a series of turns in accordance with some natural language instructions. This is also just classic reinforcement learning. We might have models which have latent variables which need to be selected in a non-differentiable way for training. And if this is the case, then you're not going to just be able to use gradient, or you're not going to be able to use backpropagation to calculate your gradients. You're going to need to figure out these things using reinforcement learning. And in the situation that we're going to talk most about today, there's situations where, again, you want to use something like a sequence level error function, such as blue. And since, again, something like blue is not differentiable, you're going to use reinforcement learning to kind of get around this non-differentiability. Okay, so we're going to step by step build up what's called the policy gradient or reinforced objective. And we're going to start by just looking at supervised maximum likelihood estimation. So in this case, in supervised learning, we know that the correct actions are in fact specified at training time. So in our supervised loss, of course, we are just trying to minimize the log probability or maximize the log probability of the correct action or Y given the input or the state X. And you can just think of this as, again, if our state is equal to X, if the action is equal to Y, and the reward that we're trying to maximize is the opposite of the loss, because of course we're trying to minimize loss, we can see that in this instance, supervised learning is just like a subset of reinforcement learning. In reinforcement learning, we call this behavioral cloning, which is itself a subset of imitation learning. Maybe the kind of RL that you're more familiar with is like the agents trying to explore, finding new ways to do things better than humans by following wherever the reward function leads. But there's a whole section of RL that just focuses on imitating expert demonstrations, which is essentially what supervised learning is doing. So just take a brief look at 12 again. We're looking at the log probability of Y, which is the correct label. Now what we can do is, next we're going to talk about self-training. This is a little bit weird at first. When I first heard about self-training, I didn't really get it. But what you're going to do is you're going to take a model that at least already has some training, hopefully a fair amount of training, and you're going to just sample from the model by feeding inputs into it, and you're going to generate Y hat. Of course, you could also just use an argmax here instead of sampling from it directly. And so you can use this self-generated label, Y hat, as an optimization objective using maximum likelihood. This is called like self-training because, of course, you're just labeling, the model is just labeling the data itself and then training on this. So on one hand, this is turning unlabeled data into labeled data, which is great. But on the other hand, of course, this isn't going to get you very far because, if you're already labeling some of your data incorrectly, you're just going to be reinforcing those errors. So this relies, at least in part, on your model having a requisite level of accuracy. But I think self-training comes into its own more when you look at sort of the innovations on it. So if you have something like co-training, where you have an ensemble of models, only when all of these models agree do you actually use that label in the process of self-training. So kind of by leveraging the uncorrelated errors of an ensemble of models, you can kind of get better self-labeled data in this case. You can also do something like adding noise to the input or adding noise to the hidden layer in your self-training. And what this is essentially doing is it's kind of acting as a regularization on the unlabeled data, because you're kind of seeing, you are presented with an example that you've sort of already seen, but then if you corrupt this input, you're actually kind of forcing the model to be robust to these corruptions. But the thing I actually want to emphasize from self-training, again, is this equation 14. And once we kind of understand the self-training objective, I think it makes a lot more sense once we turn it into the reinforce objective. Reinforce is a specific kind of reinforcement learning, which is a subset of policy gradient methods. So I might refer to this as policy gradient, but there are other forms that policy gradient can take. And there are, of course, forms of reinforcement learning, like Q-learning, which are just not policy gradient at all. So just to be clear, this isn't all of reinforcement learning. This is just one specific algorithm. And what we're going to do to get our reinforce objective is we're going to take our self-loss and we're going to multiply it by the reward. So this makes sense now. If we have the model generate its own label, and then we use the reward function to judge it as good, it's of course going to increase the probability of using this. If the reward is maybe really high, then it's going to increase the probability of this even more by taking maybe a bigger step with the parameters, with the parameter update. Of course, if the reward is negative because it wasn't a very good label that the machine applied, or it wasn't a good label or action that the model took, then of course this is going to be negative and it's going to be minimized in the future. Now, just like we were talking about before with cost-augmented hinge learning, this reward function is just a function of y hat and y. So one, this is operating at the sequence level, and it doesn't have to be differentiable. So we're free to use something like blue. Another advantage of reinforcement learning with this policy gradient objective over and above the hinge loss is that you don't actually need to calculate the probability of the true label with this p y of x. You only need to know p of y hat at x. And this can be useful if the sequence of things you did is kind of hard to retrace. You know, if you were like a robot in an environment that's changing and you took a bunch of different, you navigated through a very long environment, it might be hard to go back and try to say, well, what if you had taken these steps? What would the probability of that then? That can be non-trivial in certain cases. So the fact that you don't need to know that value is also helpful here. But with the generality that reinforcement learning offers, we also get more problems. Kind of always the case. And one of the big problems in reinforcement learning that I'd like to point out is something called credit assignment. And that's the idea that since these actions are cumulative, think like when you're doing supervised learning and just maybe predicting like labels in image classification, every time you see an image, it's a new day. You're never, the label that you predicted 3 examples ago has no impact on what you're doing this time. But if you're translating a sentence or you're a robot navigating through a maze, like the word that you gave at the beginning of the sentence can kind of affect where you are currently. It can affect both the state of the model, but also how good your translation is going to be if you have something like a long-range dependency. And so with this sort of extension throughout time, we have to worry about credit assignment. So in the best case scenario, what we kind of have listed up top here, the reward function is going to be giving immediate responses to the actions that were just performed. And this way, it's kind of easy to see, okay, A2 was a good action, A6 was a really good action. We definitely did something wrong at A4 because we got a negative reward there. But things aren't always so nice. In the worst case scenario, we just get a single reward at the end of the episode and no indication which action went wrong. We might just get a -1 after we take our final action. I think the analogy I like here is if you did a very long math problem where each part builds on the next, and you just get marked wrong, and they don't explain where the mistake was. You have no clue. You'd have to work back, and you'd have to maybe try it in a lot of different ways to figure out where your error is if the person wasn't kind enough to go and tell you. But sometimes when we're building our reward function, it just isn't possible to decide until the end of the generation process. Maybe if you're generating a sentence and the reward is whether it's grammatical or not, you don't know if the grammar is right until you get to the very end in some cases. And so on top of credit assignment and sort of the difficulties that presents, as with other sampling-based methods, reinforcement learning is unstable. Or I guess maybe here I should have put policy gradient, though I guess reinforcement learning does involve sampling and whatnot. And reinforcement learning becomes even more unstable when you have to predict a lot of different actions, because you have to try a lot of different actions out. So if your output space is a whole vocabulary of 10,000 words, That's a lot of actions that have to be predicted and have to be tried out and sort of have to be learned. But we're going to briefly cover some various strategies that can be used to stabilize reinforcement learning. First, I want to present minimum risk training. And this is a paper that focuses on machine translation and how can we line up, again, like problem number 2 from the beginning, how can we line up our training objective with the evaluation metric? So what they do is they couch this in terms of risk, which you can just think of negative reward, and risk is represented by delta. So of course, we're trying to minimize this. And they present the risk function as being, they try negative blue score, translation error rate, as well as negative miss. And these are smooth so that they don't get any like infinite or zero calculations values when they're doing these metrics. And these are also taken at the sentence level because of course blue is a corpus level metric, so they're doing like the sentence level version of blue. And what we have here is a loss function that is pretty similar to our policy gradient projective, I guess. They didn't phrase it in terms of the log here, so don't be too worried about that. But I think what's most interesting in this paper is how they're treating this S function. So what is S here? It's talking about the candidate translations that they're going to check and factor into their loss function before they perform a gradient update. So if we are just to take a single sample from the model just generates one sentence, and then we calculate the risk, or we calculate the negative blue score. This is actually just like vanilla reinforce. You know, this is reasonably fast, at least comparatively, but it's very unstable because, you know, like Graham was saying before, if it's just sampling from the model and it just generates some random sentence that's no good at all, it's not really going to be getting anything very informative. To kind of do this properly and to actually minimize expected risk, to calculate expected risk, of course, you just very easily, you iterate over all of your sentences. But as we know, this isn't going to work because your model will never make it past the first iteration. So this is intractable. So what the authors find is that when they take about 100 samples from their model, they are able to get a useful gradient signal. And this is slow. It is much slower than the maximum likelihood objective with feature forcing, but it does improve their scores, their blue scores, quite a bit by optimizing on this metric at training time using minimum risk. I'm just going to check time here. Okay, so I'm just going to quickly offer some other ways within reinforcement learning that we can. So in minimum risk training here, the main way that we were doing stabilizing is by summing together many different samples before taking one gradient step and calculating the loss. Another way to do this, or not to do this, but another way to stabilize reinforcement learning and to help reduce the variance of the gradient. And maybe this is the one case where we do get free lunch. Using a baseline is a way to actually reduce the variance without introducing a bias. So it doesn't happen very often, but this is one of those cases. And what you can do with a baseline is essentially kind of anticipate the reward for a given example, and then optimize based on the reward minus the baseline. So basically whether you're doing better or worse than expected, rather than just using the raw reward. So, you know, with the input to this model is, this is an easy sentence, you know, you might actually do it might be a pretty good translation, but you could tell that this is a very easy sentence, so you should have done even better, in which case you actually get a negative reward here. Whereas if you do so-so with the sentence buffalo, 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 you might not have done too well, but you expected to do a lot worse. So generally speaking, the model parameters are in the right place. And so this is just what your objective looks like. It's very similar to your policy gradient objective. but now it's in terms of your baseline. So the choice of function for a baseline can vary pretty widely. You can do something which is, I think, similar to like active critic models, if you've heard of those in reinforcement learning, but you can predict the final reward using some simple model given the current state. And so you could do this at the sentence level and sort of predict this, just at the sentence and apply this to all the different updates at each action. If you are looking at the individual, if you are looking at the individual elements as being their own actions, then you can do this at the sentence level and apply this one baseline for each of these actions. Or you could also do this at the decoder state level, and at each place in the decoding process, you can be predicting sort of an incremental baseline. A much simpler way to do this is you could just use the mean rewards in the batch as the baseline. I guess a sort of batch normalization for reinforcement learning type objective. Or like many other machine learning methods, you can just increase the batch size. So this is a little bit similar to the minimum risk training, but you can just sample a lot of different examples, or what we would call rollouts, using one policy, and then calculating the gradients of these, or rather summing the gradients of these together and then taking the step at once. And this can actually be a little bit inefficient because now all of a sudden, to take one gradient step, you have to run your model many times before you're doing that. And of course, the more you run your model in between taking gradient steps, the slower your training goes, even if this does improve stability. So one thing you could do is to save previous examples from previous, when I say previous models, it's basically, previous models are just like before the current update. So once you sort of update, like if you've updated your model in different places, you could use experience from back here, or use rollouts from back here. And this is nice because you're not throwing away this useful data every time you update the parameters of your model. And this can be a way to sort of, essentially get free data and decrease the variance of your updating. But this can be biased because the model is not the same as it was. And in certain reinforcement learning algorithms, this can actually be a huge problem because the data that's collected at a slightly old or slightly stale version of the model can actually make the optimization of the current parameters sort of be going in the wrong direction. It can be adding bias in this case. So this is sort of a double-edged sword in this way. Similarly to hinge loss, we can also just do something like a warm start, where we train up the model with maximum likelihood, which is a bit biased, but then switch over to reinforcement learning, right? This is the idea of let's train with the low variance model. Maybe it has a bit of bias, but once we get it to a good state, then we can fine tune using our high variance but low bias model, like algorithm, like reinforce. Of course, this only works in scenarios where you're using reinforcement learning to replace MLE. If you can't do maximum likelihood estimation, then you're stuck just using reinforcement learning. In the literature, you could take Mixer to be an example of this, where they have a smooth annealing process from maximum likelihood to a reinforcement learning objective. Okay. I'm going to take one question on Zoom about the reinforcement learning, and then if anybody else has questions, here we can take those. One person asked, can you give an example of a model or application where we choose the latent variables using reinforcement learning? I actually took that from Dan's slides, so I have to punt on this.
Yeah, so any latent variable is any time you would make a discrete decision between the input and the prediction you want to make. Um, to give an example that we've already talked about in a previous class, it could be something like if you're building a retrieval-based question answering system, a retrieval-based question answering system might use all of Wikipedia as its data source, but it can't process all of Wikipedia with BERT because GPUs aren't quite that big yet. So basically, what it needs to do is it needs to make some discrete decision about which information on Wikipedia it's going to be using. And that discrete decision of which sentences to be selected is a latent variable. So it's a variable that you don't know the correct answer to it, but you might train it jointly with the model. So you can view the retrieval model as a model that's being trained using reinforcement learning, where if the final question answering model does a good job of answering the question, then you've succeeded. If the final model does a bad job of answering the question, then you've failed. Other examples include things like inducing structure, linguistic structure from language. So for example, the syntactic parsing lecture that Hal gave is another example of that, where we were learning latent like parse trees. So those would be, I guess those would be the two stereotypical examples. The first example is we have to make some latent decision in the middle of our model for whatever reason, for efficiency reasons, for giving our model a good inductive bias. Or the other thing would be that we want to induce some latent variable that's kind of inherently interesting to us, like a parse tree. So those would be the two examples.
Yeah. And then the second question on Zoom is self-training kind of like semi-supervised learning? I would say it's more similar to self-supervised learning because I guess you're going to be working with unlabeled data, but I guess there is a transition usually from labeled data then to unlabeled data. So it's a type of semi-supervised learning.
Yeah, and like one interesting thing is I don't actually know what self-supervised learning means. It's basically the same thing as unsupervised learning.
I had a debate about this.
I think it depends on who you're talking to. But like, so if you think of unsupervised learning as learning from unlabeled data, from learning from data that doesn't have Y annotated on it, supervised learning is learning of data that only has X and Y. So you're only learning from data that always has your input and your output. Semi-supervised learning is when you learn from some data that doesn't have labels and some data that does have labels. I would say that I would say that self-training is basically a variety of semi-supervised learning. It's not all of semi-supervised learning. There's other varieties. But
yeah. And one thing I heard, I don't know if I agree with this distinction, but like unsupervised learning would be like clustering. And I guess you're not actually like learning from the data. You're just trying to find you're just trying to find patterns from it, which I guess essentially isn't different from what BERT is doing, but this person is trying to argue that BERT was self-supervised and not unsupervised.
Yeah, I don't think there's a difference. Jan LeCun can fight with me if you want.
Yeah. Pseudo labeling. I'm not sure. What would be an example?
I actually haven't heard the term pseudo labeling either, but if I just infer what it means, then probably the same thing.
Yeah. Mm-hmm. Sorry, I was having a little bit trouble hearing that. So what is model A doing in this case? Yeah. Is using alternative and a maximum likelihood objective. Okay, so the question was, if you have two models, if model A is using minimum risk training, it's like this sort of reinforced style objective, and model B is using a maximum likelihood objective with negative examples in the batch. I think, how would you be generating those negative examples? Would you be like sampling from the model incorrectly? Like, would you be forcing the model to generate like bad sentences, like kind of an anti-beam search or something, or something? So in sorry, the reply to my question was using something like these negative examples would be decided using something like a sentence similarity metric. So I think to a certain extent that would definitely be remedying, you would be remedying exposure bias in the way by sort of exposing it to these bad translations that are close to what they should be, but not quite. And you certainly would be incorporating like a cost function into this training process, or this evaluation metric. So it is addressing these things. I mean, like on an algorithmic level, it is different than minimum risk training because you're not using that maximum likelihood objective. You're not back propagating through that softmax in the same way. So what the different properties of those would be, I'm not sure, but I think like you are still addressing the same issues, just differently, algorithmically speaking.
Yeah, and to add a little bit to that, basically, there's a really popular term right now, contrastive learning. And contrastive learning is not really a new thing. It's been around forever, but most contrastive learning functions use hinge loss, like the one we were talking about here, the margin-based loss. And the margin-based loss doesn't have a probabilistic interpretation, whereas the risk or reinforcement learning losses do have a probabilistic interpretation. They're basically saying we want to minimize the probability of getting a bad translation, or we want to maximize the expected reward or minimize the expected error or something like that. So hinge losses, on the other hand, are good because you can also do things like force the margin between the good examples and bad examples to be larger and things like this. So they have a different type of interpretation, but it's not probabilistic. So I think that's a big difference. Another thing is margin-based losses can be used for everything, but they're particularly popular in things like retrieval, where you have one correct thing that you want to be retrieving and then a whole bunch of other negative things that you don't want to be retrieving. And there's a bunch of related techniques like in-batch negatives. So you have a whole batch of like 64 sentences, and one of them is the correct answer, and then the other 63 are wrong answers. So that's a good way to efficiently get negative samples. Some other concepts are things like hard negative mining. And hard negative mining is basically finding hard negative examples, like ones that look like they should be right, but they actually aren't. And that's actually very related to the cost-augmented decoding, because cost-augmented decoding basically finds the hardest possible thing where your model gives it a high score, but it also has a high cost. And you can think of that as something like hard negative mining for retrieval, where they try to find the most similar possible wrong examples in retrieval. So all of these things are kind of connected together in various ways.
I'm just going to quickly overview. Those were like the two major parts, but I'm just going to offer some quick, slightly easier ways to remedy exposure bias that don't involve using these non-MLE objectives. So as I had said before, I'm just in the interest of time, I'm going to skip over this slide. But essentially, hinge loss and reinforcement learning can be unstable and slow, even if they are addressing exposure bias and they are taking into account the evaluation metric. So while still using MLE, we can do something relatively simple to combat exposure bias, and that would just be actually incorporating the model samples during training. Like, don't just always use teacher forcing. At the beginning, we might use teacher forcing again to get the model in a good place more generally. And then once it's starting to do better, we can allow it to take previous samples from itself, so it's getting more used to the testing distribution. This one is pretty straightforward. Instead of worrying about taking samples from the model, we can just apply dropout to the previous labels, in which case, just as dropout sort of makes sure there's no one point of failure for like a given layer in your neural network. This is just making sure that the model doesn't live or die based on the previous label that it's seen. This one's quite subtle, but what you can do is by introducing errors strategically into the training data that is actually based on a sort of similarity metric, you can actually, the paper shows how this is actually equivalent to minimizing risk simply by using your maximum likelihood objective and by perturbing some of your labels. And you can kind of think of that as we're incorporating the risk function into the way that we perturb the labels so that there's a certain level of robustness, there's a certain distribution of robustness that our model is sort of accounting for during this maximum likelihood training. I just wanted to, in the last couple minutes, just try to summarize what we've gone over and some of the broader themes from the lecture. We covered structure, margin-based methods like the structured perceptron and structured hinge loss. We also talked briefly about reinforcement learning, sort of the basics of that, and how it could be used to especially remedy the second issue of not taking into account our training metric. And then very quickly, we just talked about how you can actually address exposure bias and sometimes even minimum risk without straying from the maximum likelihood paradigm. So the takeaways I'd offer from this lecture is that NLP presents some unique problems within machine learning. Of course, structured prediction comes up elsewhere, but I think predicting the sequences is very characteristic of natural language processing. You always have to be in this realm combating sort of this bias variance trade-off. And generally speaking, there's no free lunch. You can't just reduce your variance and still have no bias at all. But to keep the analogy, I would say you can get more bang for your buck. Sometimes it's okay to reduce your variance by a lot and only bias your samples a little bit. And I would say differentiable objectives are often, well, I guess hinge loss is differentiable, but like a maximum likelihood objective is just very good. It's a very good general purpose tool. And it's hard to beat it, but as we've shown, we can beat it sometimes, in which case, just keep your mind open to these opportunities when they arise. All right, that's right at the dismissal time. So I'm happy to answer any questions, but no one's held captive any longer.